The next network model is called shortest path problem. So here we have nodes. One is the origin node and the last one is the destination node. There are a lot of intermediate points and each arrow has the distance associated with it. So we can think of these as cities and the arcs are roads. Now we want to get to 10 from 1 using some of these arrows such that we traverse from 1 to 10 at the shortest possible distance. There are a lot of applications for shortest path problem. We can code a equipment replacement problem, a maintenance problem as a shortest distance problem. So let's first look at the basic model of the shortest distance problem, and then we will look at an application of the basic shortest path model. And you can use shortest path for routing traffic, internet traffic and other traffic in general automobile traffic and things like that also. So let's look at this problem in Excel. So again, we need to set up the origin and destinations and the distances that are given in the network. So let's look at the network. So we have from 1 to 2, 1 to 3, and 1 to 4, or the 3 arrows going out of 1. So we do 1 to 2, 1 to 3, and 1 to 4. Now the distances are 70, 63, and 56. 70, 63, and 56. Then the next set from 2 we have one arrow going this way. See, here is the arrowhead. So 2 to 4. 2 to 1 is not possible because there is no arrowhead here. 2 to 4, 2 to 3, 2 to 6, 2 to 5, 2 to 7. So 3, 4, 5, 6, and 7. So 2 to 4, 5, 6, and 7. And these distances are 2 to 3 is, this is 3, 4, 5, 6, and 7. 2 to 3 is 25. 2 to 4 is 19. 2 to 5 is 73. 2 to 6 is 50. And 2 to 7 is 79. And you build in this fashion, and I have done that here in model. Okay. So the distance here is input. Okay. And flow is what we want. Okay. Let's give names here. Okay. So we have nodes going from 1 to 10. So we have 1, 2, okay. So now what we're going to do is to look at the net outflow. Okay, we're going to look at this as a transportation problem, except that the starting point will have a capacity of 1 and the final destination point has a demand of 1, and everything else in between is a transshipment point. So if you go there, then you have to get out of there. So flow will be, net flow will be 0. So here the net outflow is 1. So the final destination net inflow is 1, or the way we're going to code this is, instead of looking at net inflow, we'll look at net outflow being -1. So if net outflow is -1 here, so that means we have a 1 of net inflow. So the required flows are 1 for the first one, and the last one is -1, and everything in between must be 0. Okay, now let's do the net outflow. So net outflow, so we start with origin, the node, and then we sum the flow. So this is what is going out minus sum of destination. Okay, so this will be the net outflow. Okay, what is going out minus what is coming in will give you net outflow, which should be 1 for the first origin node, -1 for the destination node, and everything in between should be 0. So set that equal, and we copy that. Okay, let's give names for these two. Now let's set up the objective function, which is the total distance. It's a sum product of these two, distance and flow. And that's our objective to maximize. So let's run solver. So minimize, sorry. Total distance must be minimized. That's our changing cell, and the constraints are that is equal to that. That's it. Solve, and the minimum distance is 198, and here is how you will go. You'll go from route is 1 to 4 and 4 to 6 and then 6 to 10. That's the shortest route possible. So let's look at the route in. So you go from 1 to 4, 4 to 6, 6 to 10. So that's the shortest route. Now we can use this shortest route problem principle in some applications, and that's what we're going to look at in the next problem.